Right, we've spent the first part of the year just so far looking at a whole variety of different functions, and then we looked at the algebra. Well, we started with the algebra, how to manipulate it and all that. But remember what we were talking about was, it's about how we're presenting the data. It was basically why we were looking at all the graphs. We plot the points, what's it look like. One of the other areas, or big areas in maths, which has a lot to do with data collection, is of course statistics. Now, probability is actually a part of statistics. You may or may not have realised that. But we'll look at the actual collection of the statistical data later, or that next term or something like that. Probability is more interesting. We'll jump straight into that. Once we've got that data, how can we use it to predict things? I mean, that's what we want it for at the end of the day. So we'll start off with pretty much a recap, probability, but then that'll lead into our next topic, which will be our first actual extension topic for the year of permutations and combinations, which personally I find quite fun. Hopefully you will too. We'll see how we go. So all right, let's recap our probability definition. So a probability is simply the chance of something happening. Okay. Now, there's a difference between experimental probability, sometimes called relative frequency, and that's when you work out the probability purely based upon data that you've collected. So you might have tossed a coin. Let's say you've tossed it 6 times and it's come up with 2 heads and 4 tails. Then we would say the experimental probability of tossing a head would not be a half, but would be, did I say 2 heads? I think I did, didn't I? So it would be 2 out of 6, or a third. My example actually is 5 coins there, and we got 3 heads. I was close. So the experimental probability would be 3 in 5. Let's say a lot different to the actual probability, which is the theoretical probability. Now, as you do more and more experiments, so the amount of data you collect gets greater and greater, then the experimental probability should get closer and closer to the theoretical probability. And if you could physically toss a coin an infinite number of times, then they would be equal. Well, clearly we can't do it an infinite number of times. So as I say, as the number of times gets closer and closer to infinity, which of course we can't do, then our experimental probability will approach the actual theoretical probability. Sample space. Well, that's all the possible outcomes. So it's also another way of thinking about it is a set of outcomes. The event space then are just the ones where a particular event can occur. So it would be a subset of the sample space. Equally likely events, well, as the name suggests, events that have an equal chance of happening. So the tossing the coin would be a good example of that. We have these things called mutually exclusive. Mutually exclusive. So only one possible outcome can occur at any particular time. So it might be that there's 2 events happening, but the result of one does not affect the other. They're totally mutually exclusive. So I put an example there here. So if you're tossing 2 coins, the fact that the first one was a head has no influence on what happens on the second one. The two events are mutually exclusive. So therefore, non-mutually exclusive events are ones where actually 2 events could happen at the same time. So you could say, I'm going to pick a number, but it could be even, but it could also be a multiple of 3. So they're non-mutually exclusive. 2 possibilities could happen at the same time. The notation we use, simply a P for probability, and then in parentheses, whatever the event is that we're investigating. So probability of a head would be P head, or something like that. If we want to work out the probability of it not happening, then we put a bar over the top. So the bar over the top saying, no, I want to find out the probability that it doesn't happen. Known as the complementary event. So every event would have a complementary event. Either it happens or it doesn't happen, basically. Okay, so some theory then. All probabilities will fall in the domain of 0 and 1. They're the only outcomes we could get. So if you're conducting an experiment and you work out the probability is greater than 1, you know you've done something wrong. Or if you get a negative number for that matter. If the probability is 0, we're basically saying it's impossible, can't happen. There's no chance of it ever happening. And then at the other end of the scale, if it equals 1, we call that a certain event. It must happen. So if all the events are equally likely, so if we're considering something, then our sample space would be uniform. And so it's nicely balanced. The probability of an event happening. Now, we've got, what's the absolute value? Absolute value of E over absolute value of S. What does that mean? Well, absolute value is a notation we use for size or magnitude. So basically, absolute value of E, we're saying what's the size of E? How many events are there in that sample space? How big is it? And then absolute value of S would be how big is the total possibilities? How big is the sample space? How many things are in there? It's not really a formula we write down that often because normally, or a lot of the times, it's very intuitive. And you say, oh, what's the probability of rolling a 2 on a dice? And you just go, oh, well, it's 1 in 6. You just write it down. Complementary events, because remember we said either something's going to happen or it doesn't happen. So the 2 events must add up to be a probability of 1. Either it's going to happen or it doesn't happen. Well, rearranging that idea, we get the probability of something not happening would be 1 minus the probability of it happening. It's all right. Knowing what the sample space is then becomes important. We need to know what are all the things. So there are different ways we could do it. So mainly we're talking about multi-stage experiments. As I say, when you're just rolling a dice one time, you don't really write down the sample space. We know it's 1, 2, 3, 4, 5, 6. But when you start doing it twice and things like that, that's when you might want to list all the outcomes to go, all right, what are we dealing with here? So the first way of doing it is you could simply create a list. So just writing down every possibility. Here's one from the 2004 HSC. So we've got a game. It's an interesting dice. Instead of going 1 to 6, it's going 0 to 5. The score for each turn is calculated by multiplying the 2 numbers uppermost on the dice. Okay. So I'll just list the sample space. There's 36 different things that could happen. I could get a 0 and a 0, so the score would be 0. 1 and a 0 would be 0, and so on and so on and so on. I could work out each particular outcome. Now the actual question, well the first question was, what is the probability of scoring 0? Well, it's just a matter now of counting how many zeros there are in the sample space. So, there's one. Oh, look, there's one. Oh, another one. Oh, another one. Oh, that's one too. Oh, yes. Oh, good. And we've worked out, okay, there's that many. So we get 11 out of the 36. There's our chance of scoring a 0. What's the probability of scoring 16 or more? Okay, 16 or more. Well, there's 16. Well, 20 is more than 16, so is 25. So we get 4 in 36. That simplifies down to be 1 on 9. There's another way, you might have seen it before, a dot diagram or something like that. So we've got a pair of dice. Again, it's a sort of common sort of probability question. Roll a couple of pair of dice. Probability they total 3, probability they total 7. So in this case, instead of physically writing down 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, we sort of draw up a little, well, I want to say graph, but it's not really a graph, because all I do then is go, oh look, there's all the outcomes. So those points, each point represents an outcome, and then you just read off the axes what the outcome is. It's essentially exactly the same as writing 1, 1, 1, 2, and so on, but I suppose it just saves time because you can just go, ooh, dot, 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 dot. That's how it's really up to you how you want to do it. But the same idea now, total 3. Well, 2 and 1 and 1 and 2, then total 3. So 2 out of the 36, which is 1 in 18. Total 7, which of course is the most common one that could happen. I don't know if you realise that or not. It also explains why, when you look at a dice, opposite faces add up to 7. I don't know if you ever realised that or not. But that's how dices are built. The opposite faces add up to 7. So probability that it equals 7, there's 6 of them there out of 36. So 1 in 6 chance. Okay. At least 3. You see that terminology a lot. You know, at least in these questions. It's like a little trigger. You go, hang on, are they trying to tell me something? Because sometimes it's easier to work out the complementary event and subtract it from 1. See, if I went and said, oh, at least 3. Oh, it could total a 3, a 4, a 5, a 6, a 7, an 8, a 9. It could total 10, it could total 11, could total 12. And do each of those individually. Heck of a lot easier to go, no, I'll work out the other one, because then there's only 3 things to work out. Is it a 0, is it a 1, or is it a 2? So I'll go 1 minus the probability, well, 0 can't happen in this one, so a 1 or a 2, just 2 things. And so we'll get 1 minus 1 in 36, because in fact, you also can't get a total of 1 if you're rolling 2 dice, if you're adding anyway. So it's just 1 there, 1 there, minus 1, 36, so 35 in 36 chance. Okay, probably the most common way you've seen of coming up with a sample space is the good old tree diagram. Also really good, as I say there, when the events are not equally likely. So those dot diagrams and listing a sample space is fantastic when all the events are equally likely. But if you get a question where they're not equally likely, how do you tell that this dot's weighted more than another dot and things like that? So let's have a look at this one. There's 30 tickets are sold, 2 prizes. Probability, someone's going to buy 5 tickets. They want to win exactly 1 prize. Well, they probably want to win 2 prizes, but they want to win at least 1 there. They'll get 1 there. So we branch our diagram. The first event's going to happen. Either they're going to win or they're going to lose. But in this case, not equally likely. So I just write the probability of it on the branch. So there's a 5 in 30 chance of winning, 25 in 30 chance of losing. So then they draw it a second time, but in this case, it does affect our probabilities, because if I have 1 on the first one, I've now only got 4 tickets left in there, because they're not going to put that ticket back in and go, see if you can pull that out again. That's not how these competitions work. So 4 and 29 are winning, 25 and 29 are losing, but if I lost, then I've still got 5 tickets in there, so 5 out of 29 are winning, and 24 out of 29 of losing. So all our outcomes, we could go win-win, win-lose, lose-win, or lose-lose, which is usually what happens, I find, when I'm entering these things. And then to work out the probability, we just multiply along the branches. There's all our probabilities. Now, at any stage, we can check, because it should always add up to 1, all the probabilities. So each of these branches should add up to 1. This win-loss should add up to 1. This win-loss should add up to 1. So anytime it branches out, those branches should add up to be 1. We want 1 prize, so we could win and lose or lose and win. Add them together, we get 25 on 87 is the chance of a winning there. Probability of at least 1 then would, well, I could go, I've already worked out 1 prize, so if I now work out winning both prizes and add them together, I could do that. Or I could again use the complementary idea and go, well, the complementary event is that I simply don't win any prizes. So I go 1 minus 20 on 29, that's 9 on 29. So that'll be our work for today. A little bit of introduction, or not introduction, we've seen a lot of it before, but a recap, that's a better word. A recap of our probability ideas.